So this is problem 14-24. Okay, there's a very famous reaction here with what's called Danishevsky's diene. This particular diene and there's a trimethylsilyl group here. O-methoxy. So again, I have my diene. I want you to notice that I've drawn it in the S-cis conformation. That's required for the Diels-Alder reaction. Okay. This reacts with a dienophile. This dienophile is called actin.
Hey, the paper is not, it's not in, it's blurry right now.
It's not in focus? Okay, that happens sometimes. Focus is on my hand instead. So tell me, did it come into focus?
Not really, a little bit more, but not really.
Okay, let me move it around a little bit here and see. I just, this image is so tiny, I can't.
It's in focus now. Thank you.
Okay, thanks. So please do speak up and let me know if that happens, all right? Okay, so the Diels-Alder reaction is a reaction that has a mechanism that's unique from most of the others that we've covered. The reaction mechanism is a concerted reaction. Now, in chapter 15 and 16, we're going to learn about aromaticity and benzene rings, and we'll see when we do that that there's a flow of 6 electrons, and this will be reminiscent of benzene. And so what we're going to do here is we're swinging out this pi bond. It's going to end up making a sigma bond here. This carbon, of course, has 8 electrons, so it's got to lose 2 if it's going to pick up 2. So this pi bond swings out, and it's going to end up making a single bond here. And then the same thing, there's a hydrogen on that carbon, so it has 8 electrons. So it has to lose 2, and of course this carbon lost 2, so this pi bond is going to swing down to make a double bond right here. So let me number these carbons. 1, 2, 3, 4, 5, and 6. And so then when we draw the product of this, that's going to make a 6-membered ring. So first I'm going to draw a 6-membered ring. Okay. Then recognizing that there's atom 1, it has an aldehyde on it. There's 2. There's 3. It's a CH2. 4 has an O trimethylsilyl on it. There'll be a double bond here between 4 and 5. And then atom 6 has an O methoxy group. Okay, now that is the Diels-Alder product that is obtained from Danishevsky's diene in problem 14.24. They then show some further transformations, and they're asking you to get back to this. Let me point out a couple of things. First, the dienophile. The dienophile has a strong electron withdrawing group on it. And the diene, these oxygens with their lone pairs, have strong electron donating groups on them. And this is the typical electronics for a Diels-Alder reaction. Okay. And we see this pattern many times over. All right, so key things: we need a dienophile. We form a 6-membered ring, a cyclohexene ring. It has a double bond in it. So anytime you see a 6-membered ring, you should think Diels-Alder reaction. Even if it doesn't have a double bond in it, of course, we know by hydrogenation we can remove that double bond. So you can put that double bond back when you're thinking about this in reverse. The S-cis is the conformation of the diene that's required. And with Danishevsky's diene, ordinarily we can turn this dienophile over and we get another diastereomer, but in the case with Danishevsky's diene, it's selective for this particular geometry. And that has to do with the polarity of this beta carbon, alpha beta to the carbonyl, alpha beta. The beta carbon is plus, and with this strong oxygen atom, strongly electron donating, I'm going to redraw this so that I can illustrate. You see, I can draw a resonance form here where I push the arrow. Now this would give me formally charge separation. But what this means is that this carbon has a very significant partial negative charge, and the negative and positive attraction give you selectivity in reactions with Danishevsky's diene. All right, so that's a little bit of review of a Diels-Alder reaction.